thank you, Chikeki, for an invitation. It's really a great pleasure for me to present the results of my latest paper. And this is the first time I'm showing these results. So these they are going to be in a paper in the next few days. And the topic is the development of theoretical tools for radio searches for dark matter. So since I know that many of you are not familiar with this topic, so I figure I could bring you into context. And the idea is the following. So you have dwarf galaxies where you have dark matter particles that can annihilate or decay. And then they will produce electrons and positrons and will be then deflected by the magnetic fields in the galaxy. And, you know, charged particles in accelerated charged particles emit radiation, and this radiation can be captured by telescopes. But there is a big issue here, and the point is that there are enormous uncertainties in the description of this phenomena. On the left-hand side of the slide, you can see the results of Fermi on constraining the annihilation rate for this particular BB bar model. And there, so you have uncertainties that are order 10%, maybe order 1, that doesn't matter. The point is that if you compare them to with the right plot on the slide, which are the results of a paper I got out with the Law for Collaboration last year, so you see that there are very large uncertainties. And okay, why is the question that you might be asking yourself? And the thing is that these signals are very sensitive to the unknown magnetic field in these galaxies. So we don't know, we haven't measured the magnetic field in these galaxies. And this is a technical problem that is, so it doesn't mean that the magnetic fields are weak. They can be even strong, but it's really difficult to measure. And then this is the other question, whether how many of the dwarf galaxies, satellite dwarf galaxies have order micro-Gauss magnetic fields. So of course, the ultimate goal in this research program, let's say, is reducing uncertainties. And this is a task that requires both theoretical and experimental efforts. So from the observation point of view, of course, if you carry out deeper and deeper searches for diffuse emissions in these galaxies, you will be able to constrain the magnetic fields, star formation rates, the sources of cosmic ray electrons, in particular annihilation can be a source, dark matter annihilation. And this in turn will allow you to, or us theorists, to model and simulate the evolution of magnetic fields in these galaxies. But if you turn the page around, so of course, theory can guide experimentalists in improving their strategies in searching for these diffuse signals. And this is what this work is about. So I'm not claiming that in this work I'm going to reduce any uncertainties, but this is definitely a step in that direction. So for their motivation, of course, complementarity and the fact that there are several big experiments, radio telescopes and interferometers that have shown interest, and there is a bright future with the SKA. Maybe some wishful thinking. So if, say, the CTA discover dark matter, then you could use these searches, these radio observations, in order to constrain magnetic fields in these galaxies, which is a very cool application. So I don't want to overwhelm you with technical things. So I'm just gonna show you what the model the transport model is about. So there you only assume spherical symmetry. You assume stationary conditions, and then you're left with a model with a few parameters where you have a normalization of the diffusion constant, this spectral index, so the magenta parameters for energy loss parameters. So you only assume that there are losses because of inverse Compton scattering with the CMB and synchrotron. And for the source term, so just for concreteness, I consider here the standard S-wave self-conjugated dark matter annihilation. And the other parameter is the radius of the halos. So which defines the volume of the diffusion zone. So this equation has you can solve it analytically in terms of Green's function once you introduce this Zidovsky variable, this lambda that you can see here. Hopefully you see my cursor. And so far people have considered the solution, the first solution you see here in gray. But the novelty of this work is that we consider another representation of the same function. So what you see here is the same function, but in different expressions. And interestingly, so you see that the Zidovsky variable, this lambda, appears in the denominator in one of the Green's functions and the numerator in the other one. And so this is it's crucial in what I'm going to discuss. So yeah, more theory, so I'm not going to discuss the mathematical details, but we identified a couple of regimes where so simplifications are possible. And so physically, I can say, so one regime is where the electrons, the cosmic ray electrons are created and they don't diffuse much, so they are basically lose most of the energy in situ and they emit their synchrotron radiation. So the second regime, it will be clear in the next slide. Basically diffusion washes out any information about the origin of these electrons. And the third regime is the case where diffusion happens so quickly that the electrons don't have time to lose their energies. So these three regimes, they have something in common, and this is a very nice property that the emissivity and all observables, so the brightness and so on, can be written as a product of a halo function and a spectral function. The spectral function is the same for all regimes, but the halo function depends on the regime. So in the regime A, so it's you have this for annihilating dark matter, this rho square that is reminiscent of the J factor that you are familiar with in the gamma ray case. So as I mentioned in the slide before, in your regime B, the brightness, or in this case, the emissivity, has a universal dependence on R. So it doesn't know anything about, it washes out, as I said before, the information about the dark matter density in the case of annihilation. In the regime C, so you have a bit more complicated expression, but so we computed this for many cases. We were very comprehensive, so you will see it very soon in my paper. We also managed to develop numerical recipes so that you can get the exact results in a very computational economic way. And these are these black lines that I'm showing here in these selected examples. So on the left panel, so you have a leptophilic model of say 550 GeV. And on the other two panels are much heavier decaying dark matter in the TeV range. So what you can compare there is the black, for instance, in the first plot, so the leftmost plot, you see the black line, how well it approaches the regime A approximation, so the result from the regime A, which is this blue dashed line. And in order to make these comparisons quantitative, so what you want to compare is the flux density, which is this integral that you see here. And if you're okay with sacrificing 10% accuracy in your computation, then you might feel okay using this approximation. And if you want to compare the shape of the profiles, so then you can compare numerically the half flux radii of every, and this, so I also developed the methods to compute them also in the exact case. So this brings me to the last part. I have 1 minute, but this should be enough. So what is usually done also in gamma rays, so you pick a particle dark matter model, annihilation, decay, then you pick the final state and the hard final state, so to speak. You model the dark matter halo, depending on what is a model that best fits the dwarf galaxy, and then you have two possibilities. So brute force, so you just take all parameters and you scan on this 5-dimensional cube. And then your dark matter signal is gonna be the product of the annihilation rate and it's a complicated function of these parameters. Then you test the model, and this allows you to place bounds on the annihilation rate for every point in this 5-dimensional cube. And in this work, so we realized that there are a lot of degeneracies in the problem, and so that you can actually only scan one parameter, the angular size of your signal. So your signal will be a normalization times the halo function that I provide, and then you can test a model using that parameterization. You place bounds on the normalization, and then you translate those limits. So the limits that you obtain on this normalization into limits on the annihilation rate. So this is my last slide. We also showed a formula in order to estimate the limits if you only have, for instance, a noise level of an observation. And so the formula looks like this. And then is taking, in this case, it's the flux density halo factors that in this case for NFW. So then you pick the parameters. For instance, I took them from Kohei's paper. And so then you can predict some limits that you see here. And I also comparing here the shapes of the profiles without showing you the shape of the emissivity. I can compare them by means of this half flux radii. So I can conclude now. So in this work, so we developed this new method, which is very nice and practical. So we identify the characteristic regimes where we can do approximations. We tested this approximation, and we propose a new strategy that is much simpler than this brute force strategy that I talked before. Thank you very much.